Today I will talk about applied machine learning, and I will talk about how we apply this to crystal structure, but also healthcare. And I will hopefully convince you that these are quite, the techniques are applied are quite similar. So we will start with some machine learning basics, then we go to application in physics, application in healthcare, and then we'll finish with the conclusions. So first, I would like to acknowledge the people that I work with in the last few years, and so in particular the Fritz Haber, and I will present the work that has been done together with my PhD student there when I was there, so Andreas Leiterer, and then Bayer AG, where I am there now, and also the faculty in Università Cattolica. I'm a proud alumni, so everything I know about physics, they taught me. So thanks a lot. So let's start with some machine learning basics. And so what is machine learning? So machine learning is a study of computer algorithms that improve automatically through experience. So I really took the definition from Wikipedia. And what is important to notice is that the model is going to be trained on sample data without being explicitly programmed to do so. So that's where you usually use machine learning. And why does it make sense? In some cases, it's because in some cases, often actually in real life, it is difficult or unfeasible to develop conventional algorithms to perform the task you want to do. And in physics, you can think about it as if you want to calculate system properties that are too complicated, too computationally costly to get with other methods. Let's say you can always show the Schrödinger equation direct in principle, but in practice you cannot do that. So machine learning can be very helpful. And also you can see it in a way that at the level of granularity that you are interested in, the mechanism cannot really be predicted. So imagine that you want to predict the superconductive temperature of a material just with chemical composition. I'm not saying that this is possible in machine learning. I'm just saying that machine learning can be useful where a clear algorithm to go from the input to the output is not really available. And so let's go a bit into details of this sentence. So machine learning algorithms are used in a wide variety of applications where it is difficult or unfeasible to develop conventional algorithms. So what I actually mean by that, I think it's useful to look into that. So think about it. So what makes a dog, right? So if you want to make a conventional algorithm, you need to specify rules to say when a dog is a dog. Or in physics, you need to have a physics law for that. But if you think about, if you start defining rules, then you say, okay, the dog has 2 eyes, 1 mouth, 4 legs, and 2 ears. But that's not really enough, right, to define a dog. So you say, okay, now you should have a cute nose, great sense of smell, and you know that it becomes ridiculous, right? So it's impossible to define rules, to define what actually a dog is. And that's where machine learning comes into play. So what you do, you imagine you want to train a computer vision task, and you tell the computer, you give a lot of images of a dog, and you say, computer, that's a dog. And then you give lots of images to a computer that is not a dog, and you tell the computer that's not a dog. And the power of machine learning is that you can really there are algorithms, in particular lots of deep learning algorithms that can predict. They can work and learn from data and then predict if a new image is a dog or not. And this is what is usually referred to as supervised learning. So you have a clear task to perform. You want to define, is that a dog or a cat? Or in physics, maybe you have FCC, BCC, or HCP, which you get a structure in, and you want to decide what is the crystal class. And to do so, you need to have labeled data. So you need to tell a computer which is which. And then at the end, you just have a classification task. So you say how many among the classes that are available, which one is the right one. And so in this talk, I will present the work we did that's actually from yesterday is on the archive. So we will we use supervised learning for crystal cluster classification. And but we will also see unsupervised learning. And that is quite an explored area of machine learning. And there you have the task that is not clearly defined. So you want to find patterns in data, anomalies, explore similarities. That's what people would say. So and it's very open, so you don't know actually what you're looking for. And this, of course, makes it very difficult because you don't know how to, it's difficult to quantify how good you're doing. It's with respect to instead the supervised learning when you really have accuracy, did I predict correctly or not? That said, I think it's quite cool in physics because you can discover something new and that you don't know yet, and you don't even need to know what to ask beforehand before you do the analysis. And in this case, I will in this talk will present examples of how we reveal grain boundaries and structural regions in experimental data. I will show you in a moment. And then we also see how you can apply similar techniques to discover key topics from real-world medical inquiries. That's the work that I've been doing at Bayer. Okay, so great. So let's start with the physics part. And so let's say what do we want to do? So the goal is to, given a defective crystal structure, you want to assign the most similar prototype. Imagine the prototype can be FCC, diamond, BCC, HCP, but we'll do much more. We'll do 108 classes. And the state of the art out there it can be divided into two groups. One is space group based, so when you really want to predict the type of the space group, and then you have and these are the forefront SPGLib and AfloSim, and that is by Stefano. And then they can do really a lot of space groups. The methods are not robust, but really by design. That's on purpose because you want to really be fine in classifying when the space group is a space group, right? If you're missing atom, the space group is different, and so that's why they are not robust by design. And then we have a local structure base where you really look at neighboring of atoms, and these are some examples. And there they are very robust, but they have a limited number of classes, so in the region of 4 or 5. And so you can imagine that there is some space to do something in between, depending on the application, especially considering that with experimental data you might have noise in the position of the atoms that you might get from experiment. So therefore, our goal is to have a methodology that is robust, and there's a lot of number of it can treat lots of classes. In particular, let's say lots of material types and 2D material. So for example, carbon nanotubes and bulk materials. It should be threshold independent in the sense that you don't want to put threshold beforehand to define when a material belongs to a class or another, which is impractical with large databases. We also want to classify single and polycrystal system at the same time, and we want to estimate the uncertainty, so when we are uncertain about our predictions. And we also want to use this for exploratory analysis, so doing unsupervised learning. So, and that is, we call it this method RI, and we'll start with the single crystal classification. So, and how does it work? What's the high-level workflow? So in input, you have a single crystal, and that's the input of the model. Then you need to represent that, because a computer will not understand the crystal. You need to represent it in a sensible way, and the computer will understand numbers. So what you have to do, you convert the two-dimensional structure to a vector, and you need to do it in a meaningful way, so preserving the symmetries, for example. And from that, you will have from a single crystal, you will get a vector. After that, you want to have from the vector, remember, we still want to classify which is the most similar prototype to a given structure. So you want to learn a mapping that goes from a single crystal to the actual class that you're interested in. And for that, we will use Bayesian deep learning. And then at the end, you will have as an input single crystal, as an output you get the prediction class, but also the uncertainty, which is usually not returned in lots of applications, but we think it's quite important to do so. And so you will have an output. Let's say, okay, that's a rock salt with some probability, and then some uncertainty quantified by the initial information. So that's the idea for the single crystal. And so we'll start looking at the representation part. This is not our work, so I'll go quite briefly. So the idea here is that we want to represent, as I said, to transfer the 3D structure to a vector, and we use the so-called SOAP descriptor by Gabor-Xanin group. So the idea is the idea is quite simple. You sit on each single atom of the structure, and you look at your neighborhood, and then you place on each atom that in the neighborhood Gaussians, and then you sum these Gaussians, and you're able, and you expand them in spherical harmonics, and it turns out that you can compute analytically a representation that is invariant with respect to rotation. And so that is SOAP in a nutshell. For the purpose of our talk, the only thing to know is that you have an input structure, and then you represent it in a vector, that it is invariant with respect to rotation, translation, and also permutation of atom of the same species. And you transform that to a vector therefore in a principal way. Other representation can be used. For us, doesn't really matter as long as we have a starting vector that represents the structure. And so now the part that is very important is when you train machine learning is the data, right? So we built a training data from various set of crystallography prototypes, and we will consider 108 classes. And we will have elemental solids, so we'll include all experimentally observed structure. We up to 4 atoms in the unit cell. We'll take it from Aflo, from Stefano's work. Yes, that's very instrumental for us to start. These elemental solids really we include all of them apart from monoclinic and triclinic because they have very low symmetry. And that is we take from Aflo. And then we have the binaries. So we use the 10 most common binary according to Pettiford, plus the L12 structure because it's important for nickel-based superalloys. And this we also take from Aflo. So I really want to thank Stefano because, when nobody knew what big data was, he was really already starting populating his database, and it's really enabling lots of people to do research. And then two-dimensional materials, we take 46 of them, so quite extensive library. And then we also have ternary and quaternary. That's mostly for proofs of concept. So we take 6 perovskites and 6 quaternary chalcogenites. And then we have carbon nanotubes, again, for proofs of concept to show that we can also deal with a more exotic structure. And we have 12 carbon nanotubes that we just generate. And this gives 108 classes. So it also is extendable because it's a deep learning framework, so you will have just more classes. But that's what we classify. So now we have single crystal. We built a training set. So which kind of model do we use? So we use deep learning, and in particular Bayesian deep learning. So why we choose deep learning? So deep learning is we'll choose neural networks with lots of layers, and that's what deep learning is. And why we choose that? Because the good thing about deep learning is that it's able to learn underlying feature from the task, and it does it automatically through a series of layers. So we get the input structure, and then the network will automatically calculate the representation through some nonlinear transformation, and then at the end arrive at the classification decision. And this is very successful in lots of computer vision, machine learning, and natural language processing tasks. And it is being shown really that the underlying features are learned. And this is from image classifications from 2009. So you see that the network, when you start, it just learns very low-level features. And then as you go down to the layer of the network, you will have mid-level features that are learned, and then at the end, high-level features, like faces, for example. So you see that the network really combines the input in a smart way to arrive at the good classification decision. And we also show in a work that we have done that this also happens with material science. So, and this fact that the underlying features are learned, we come back to the end of the talk when we use unsupervised learning. So that is deep learning. So deep learning, you get one output. So let's say you get an input structure, and then you get one output as a classification. But the problem with that is you want to define an uncertainty. So that's why we use Bayesian deep learning. And so the idea is that we have, instead of having one network to predict one output, we get lots of networks that are slightly different, and then we look how how these outputs, if they are all the same or they are different, and we calculate the mutual information for that. And that's how we evaluate the uncertainty of the model. And so maybe going to the details, this is work by Yaringal at Cambridge back then and now at Oxford. So the idea is really to get, instead of one prediction of deep learning, you get lots of different predictions multiple times, and you just randomly drop new units in your network. So you get slightly different network that will predict your output. Then you get a lot of predictions, and then you can estimate the prediction looking at how, if they all agree or not. So if they all agree, the network is more confident. If they are more disagreeing, then you say you have a high uncertainty. And you can quantify this based in information theory on mutual information or predicted entropy. So how disordered these probability predicted are. And it has been proven that this is actually using dropout, so dropping these units actually approximate variational inference. So that's what Yaringal did. So now we have deep learning and Bayesian deep learning, and we apply to the task of crystal structure recognition. We train on pristine structures only, and then we predict also on defective structures. So this is what we show here. So we have the pristine, that means perfect structures, and then we randomly displace atoms, let's say by 1% of the bond length up to 4% of the bond length, and then we have missing atoms. So we remove randomly 1% of the atoms up to 20%. This is a lot of displacement. It's not physical, but if you imagine that you get it from experiment, that takes it can happen due to the uncertainty of the measurement, for example. And here you see that space group base, like SPG-lib, it's not very robust, as I said before, by design. It's not because it's really because you want to have the correct space group. And if one atom is missing, you don't want to have the space group that would be if the atom were there. And here you see that you don't get any meaningful prediction with robust. With lots of atoms missing, and then you have a local structure base where they are very they are very let's say robust, apart from missing atoms that they really go. This I should say this is the accuracy. I'm sorry. So this you see that you have very low accuracy in this region, but the problem is that they treat a few classes. And so what we did with deep learning, and this is what we did here, is use deep learning to really be able to predict all the classes, that in our data set, plus really being robust for that. The downside of that is that you need labeled data for training. And our labeled data comes again from a flow or SPG-lib at the pristine level, right? So where here they are all 100%. So that's the benchmarking. And then I think it's exciting also to show some experimental results. So this we have STM images, so of graphene here, that's the input. And then what we do, we reconstruct the atomic positions using actually a deep learning framework that was published in 2017. So we are able to go from this structure to actually the coordinates. This is not our work, we just use this. But then once we have that, we can apply our methodology because we don't need the unit cell. We can just apply that to the full crystal. And you see that we are able to correctly recognize it is graphene in both cases, even though there is some noise. Also imagine that there's an image very distorted, that then you apply deep learning on that to get the position. And so that is, and also you see here, it's hard to see, but you see you have pentagons, for example, there's a defect there. And you're still able to classify that correctly. And what is pretty cool, we got excited about is that the second and also the second candidates, the probability 99% of graphene, but then 1% of this material that is also hexagon. So the network kind of learns also the geometry, and this you can also see that also in this case is more distorted, so you have a lower probability. And actually, the cool thing is that the top 5 prediction are all monolayer that we get from the network. So when the network is wrong, it also makes sense when it's wrong. And here you see that the mutual information is much higher when the distorted structure. So it's really that mutual information kind of quantifies the disorder in the structure. This is for the single crystal, but then we can also apply that to polycrystal. And the idea is very simple. So you get a structure, could be a slab, but could also be a 3D structure, and you take a box, you slide this box through a material. And for each position, you just get the atoms that are within the box, and then you apply the prediction that you will strain for a single crystal. And then at the end, you put all the boxes together, you see, and then you get a classification. So one box here, you take it out the atoms that are there, and then you will get the prediction for one pixel. And that's how it works. And you can do the same with a bulk. So you just have to slide the box in 3 dimensions. And then in this way, you can have a true 3D maps where you have a classification for each slab. So that is how we do polycrystal classification. And then there are some synthetic. Let's start with some synthetic examples that we did, because with synthetic examples we know that like what to expect, and so we want to test the algorithm. So we make this structure. It's really just a synthetic structure with 4 different type of crystal structures, and then we know how they are because we generated them. So and then we apply this classification. So arise, so train on single structure, single crystal, and then this striding pattern matching we call this striding of boxes, and you see that we are really able to recognize the regions. And what's exciting too is that if you plot the mutual information, you see that the network is uncertain at the borders, so you automatically detect grain boundaries. And what we also did is that we did it in 3D. So an example where we get to the box and we have 2 phases. So one phase when you have a nickel aluminum, and then here you have these are phases that are important for superalloy, and then you have one phase where you have the atoms that are really ordered in these structures to chemical compositions that are really in the right places, and then you have a random FCC matrix where you have AL and I can be really just randomly distributed. And this is quite hard because you have the same lattice, and the only difference is that this is disorder from a chemical perspective, and this is order. And we do that, and we make at the center we get the AL1-2 phase. We make this system, and then you see, and then at the end and around we have the disorder part, and we are able to detect that, and the disorder part is classified as FCC as you would imagine. And this you see. That you can see actually that for pristine and also defective, so 20% of the atom missing and 1% of distortion, you're still able to do that. And that's pretty cool, I think, if there are 3D structure in experiment to really look at this precipitate. And so this is for synthetic examples. Now we also went to experimental example, STM, and we use images of graphene. And now instead of having one classification for the whole system, we can also ask ourselves, let's have a classification for lots of different places in the image. And that's what we did. So you have, this is again STM, we get the coordinates through the deep learning framework that we took from other people, and then we apply our method, and you see that we correctly recognize graphene, and at the border, actually at the grain boundaries, we get MNS2. So this is, and MNS2, I'm no expert, but it looks like this. And if you think about it, you want to rationalize a little bit. If you look here, there are kind of pentagon structure at the grain boundary. So that makes sense too, that MNS2 is actually predicted at the grain boundary. And most importantly, you see here that the mutual information is really higher at the grain boundary. So you are able to automatically detect the grain boundary, where from this picture, maybe you can see it, but it's much harder by naked eye. And then what we also did, we apply this to electron tomography. So atomic electron tomography is a new technique that is able to give you 3D structure and chemical information with atomic resolutions in some systems. And so what we do, we really take the structure from the repository, from these people, from this work, from nature, and then we have a iron platinum nanoparticle with 23,000 atoms with 3 different annealing times. And then what we ask ourselves, we have the uncertainty from the prediction. So what we do we look at the uncertainty, because we expect that when there are 3 different annealing times, you will have crystal growth from across time. And this is actually what we see. So what you plot here, the mutual information that we get from our procedure. And here you see that from 9 minutes to 26 minutes, you see that this black part, so black means a low mutual information, so low disorder, while yellow here means high disorder. And you see that it is from 9 to 26, you will see that there are regions where of more order structure. So you see that you can kind of think that these are regions where there is crystal growth there. So this tells us that from a qualitative perspective, that the mutual information decreases for larger annealing times. We also have more plots and more histograms also in the paper, in the supplementaries. So that means that mutual information getting from Bayesian deep learning can actually correlate with crystalline order. So thinking further, you can also think about having AI-based order parameter, maybe for nucleation dynamic studies from this. So that is about supervised learning. And then what we ask ourselves is, I told you, right, the network is learning the representation as you go through the layers. And now we ask, can we get some insights looking at this internal representation that the network got? Of course, we have, we don't know what to ask, right? We don't know what to look for, so we can use unsupervised learning. And the procedure is quite simple. So we extract the internal representation of the network, and then we have, you remember, we have a structure that is mapped to a vector, and that's the input. Then these vectors get changed, and then you have internal representation. We can use these vectors that are learned by the network and then perform clustering in a high-dimensional space. And you can imagine that points that are close to each other in this high-dimensional space, that will be clustered together. And then at the end, we project in 2D, and that's just for visualization purposes. We do this trick on our Polycrystal, where we know the answer. And you see that we really find four clusters. Although we never use the prediction, right? We never use the supervised part. We literally said, okay, let's get the structure. We don't know anything. Let's apply unsupervised learning, and we recover that we have the four grains. And also, you see that we also have an outlier region, so where points that are not classified they are not belonging to any cluster according to the HDB scan algorithm, that they belong to the grain boundaries, which totally makes sense. So this we knew, right, the answer, but we wanted to check if actually the unsupervised learning could work from the internal representations. And then we apply this to the nanoparticle from this Nature paper. There we didn't actually know what to look for. This is the structure that it is L10 phase, and what it is. So you have iron atoms and platinum atoms, and the distance between this. So the neighbor distance between these two type of systems, it's equal when you don't have distortions. And but when you have distortion, well, it's not going to be equal. So what we did is we applied the internal representation, the clustering high dimension, and then we got out 7 clusters plus some cluster of outliers, and so that's how the map looks like. What we did then is say, why are these clusters found by the network, right? And because it's not apparent, so we really didn't know why. And so what we did, we plotted the distance between the difference between the Fe and the Pt atom. And you see that actually this cluster, when you take the average of you look at the counts, so you will see that different clusters that they are found by the network are really having different. They have a delta D that is different from 0. And you will see that the prediction within the cluster, so the histogram within the cluster is more thick. When you look at the outliers, it's really just broad, which means that the network really, you can extract some information from there, because these clusters really they correspond to substructures that are distorted in different ways. So there's a trend here you see from that this delta D grows, of course, and this was actually not known before. I'm not saying that it's usual. I'm saying that with unsupervised learning, you can find something in the data that you didn't think about. So, and this is concludes for the physics part. And so now I want to talk about the part in healthcare, and we'll show you that it's quite similar in the supervised learning part. So now here we have the task is that we have medical inquiries, and we now switch gear completely. So I will tell you, you have to know that pharma companies really receive millions of medical inquiries per related to their drugs, and these drugs, these questions are really like, can I have more information regarding a drug, or if I take this drug with another drug, do I get serious side effects on similar things? These inquiries come from patient and healthcare professionals, so they could be from doctor or nurses, and they can, they told you they can be about interactions, availability of drugs, and side effects, or maybe comparison with competitor products. And if you think about it, these are you can extract, if you think about it, that you have a lot of them, you can ask yourself, can you extract useful insight from that? Because if a lot of people are asking the same thing, maybe there is something going on there. And you can imagine that you can detect product quality, supply chain issues, or maybe anticipate treatment trends, or maybe improve your educational material, or maybe even change the treatment. Maybe doctors say, can I take this drug instead of can I give this drug to my patient instead of once per week, once every 2 weeks? I don't know. So that could also be something that you can actually get from these medical inquiries. But there are a lot of them. It's nearly impossible to look at them all, right? Bio receives 350,000 inquiries per year. And of course, they are always replied to, so that's what the company does, and there are lots of call centers to do that. But really have an insight on all the questions asked in all divisions that's impossible from an analytical perspective. So, and that's the goal here. So the goal is really to extract topics from these questions. And if you think about it, it's quite similar to when I show you that you have a deep learning network and you want to extract minimal, let's say you want to extract the clusters that are within the representation. And we'll do that in an automatic way. So I will skip that. So the idea here is you have a part where you have the medical inquiries, and you will apply preprocessing, where you say, okay, now I have a text and I want to represent it and make it to a vector that makes sense. And if you think about it, it's very similar to what we've done before. So we have a single crystal, and then we represent that in a vector. And we want to do the same with text, right? You have a text, and the computer doesn't understand text, but understands vectors. So therefore, you will have this mapping and this representation. Back then was based on physical properties. Now will be completely based on deep learning. And how people do that? Well, it's quite clever and yet quite simple. So if you think about it, the word meaning is given by the words that frequently appear close by to that word. And this is actually something known that was something around for a long time. It's called distributional semantics. Let's have an example. So here I have 3 sentences, and you say, and if you read those, you can, and there's one word missing here, you can guess that you can actually complete that and say, like this is a word that should fit in that context. So here you see 26 minutes 11 seconds is the word for the 10,000 meter man. So I deleted the from the production database. So you can ask and you can say, okay, no, this is a word record. So in the same way, you're able to fill in the gaps. That means that the meaning of the word can be guessed from the neighboring words. That's the whole idea of semantics, and turns out that deep learning can do that. and it was from 2013, word-to-vec models, and now BERT-like models that are developed at Google. They are doing this, and you can learn a lot reconstructing the input. Not only think about it. So if you have Stanford University, it's located in Stanford. You mask that, and then you ask the network to predict. Now the network will learn trivia questions, or maybe if you have the woman walked across the street checking for traffic over her shoulder, that means the network needs to understand that this her is referred to the woman, right? You could also, if you don't understand anything about language, you could also say over his shoulder, right? But here is woman, so it will be her shoulder. So that is how, like, it's just a slight, it's just give you an idea of why people can train deep learning models, and just masking the words and then learning the meaning of the text. And the good thing is that you don't need any labels here, because you just have text and you mask words from it, and then you just to predict these words that you mask. So you don't need any label data. And it turns out that neural networks can learn that, but it takes a long time, so like hundreds of GPU days. But the good thing is that the people that do that, they make these models available for free, so you can just use the networks that are trained to make this representation from input text to vectors. Then I'll skip that, just to know that BERT is actually used in every Google search, so NLP is really affecting your life, let's say. And for us, we just use a biomedical embedding, so an embedding, a representation that is learned through from medical text, from PubMed. So it's kind of the archive of biomedicine, and we use site spacing so to do this mapping. And then once we have this mapping, right, we are just clustering these inquiries that are represented by a vector now, and we can cluster them together. Again, it's TB-scan, and then we just return a number of topics that make sense. We don't define that a priori. We just give a guidance for the granularity of the cluster. That is, TB-scan is able to do so, just to tell how granular you want the cluster, and then the number of clusters will be determined automatically. And then I'm nearly the end of my talk. So this is the example for the discovered topic on Steve Arga, which is regorafenib, which is an oncology drug. So looking at all the questions that we got from all the doctors and patients, and then we were able to automatically find the topics that are really emerging from these inquiries. And you see that they kind of make sense. So there's a topic about if people can take the medicine where there's fat, or like about a meal or a diet, or how they store it, or regarding clinical trials on that, or genetic testing. People can get genetic testing for that. So it really makes sense. And this you can just do it automatically. Instead of going through thousands and thousands of questions, you get a list of 100 topics that make sense. And so this is actually live in Bayer since December 2019. And you can also do a bit more. So you have the topics, and now you can even plot them to a map and say, to put in 2D for people to see. And then you will see that the topics that are similar to each other will be close to each other in the map. So here, for example, you see cause toxicity liver treatment, liver effect. So we generate the title automatically if you are wondering. So it's really all automatic. They are close to each other. So it's also helpful for the people to have a view of the inquiry that we are asked. And and then I will conclude with some reflections. So machine learning is really flexible and can be applied to a lot of domains. Same techniques go from crystal structure recognition to medical inquiries, and supervised and unsupervised together can really increase what you can do. And we show I show you two applications, one in crystal structure. So, and then you also have the code there. We are preparing a tutorial on that. So if you're interested in using that, it will be in a couple of weeks. You can just use it out of the box without installation. And then we also show some work that has been done at Bayer. And for that, I want to thank you for your attention. And I'd be happy to take any questions.